Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on complex analysis, power series lecture number 8, in which I will state and prove the Laurent's theorem in complex analysis. Firstly, we state Laurent's theorem statement. Let function of z be analytic in the ring-shaped region D. This is ring-shaped region. Bounded by two circles, two concentric circles, C1 and C2 be two circles, and the region between two circles is denoted by region D. The radii of circles be rho 1 and rho 2 respectively. Radius of the circle C1 is rho 1, radius of circle C2, smaller circle, rho 2. Here rho 1 is greater than rho 2, and let Z be a point of D, then function of Z equal to sigma n equal to 0 to infinity a n z minus z naught whole to the power n plus sigma n equal to 1 to infinity b n z minus z naught whole to the power minus n, where a n equal to 1 by 2 pi I integration along the circle C1 function of xi by xi minus z naught whole to the power n plus 1 dxi, bn equal to 1 by 2 pi I integration along the circle C2 xi minus z naught whole to the power n minus 1 function of xi dxi. Now we prove this. Prove. Let function of z is analytic in the ring-shaped region. This region is D, bounded by two concentric circles C1 and C2 with center Z naught. This is Z naught be center. One circle is C1 and second circle is C2. The region between these two circles is denoted by D, and function of Z is analytic in this region, means function of Z is analytic at all points of this region D. Given that radius of C1 equal to rho 1 and the radius of circle C2 equal to rho 2, where rho 1 is greater than rho 2. Let this is number 1. Let we make a cross cut LP. Here L, here P, and let we give some names of the points on circle C1 and C2. Let here we give name M N, here Q, here R. These names are M N Q R. Since function of Z is analytic in the region D and Z be a point in this region, therefore by Cauchy's integral formula, function of Z equal to 1 by 2 pi I. Now closed curve be L, the closed curve be L M N L P R Q P L. L M N L P R Q L. Arrow will be like this, and here arrow will be like this. Function of xi by xi minus z d xi. Here xi be the variable point on this curve. Let this is number 2. Imply that function of z equal to, we divide this integral in some parts. 1 by 2 pi I integration along the curve L M N L. L M N L. Function of xi by xi minus z d xi plus 1 by 2 pi I integration along LP. Function of xi by xi minus z d xi plus 1 by 2 pi I integration along PRQP. PRQP. Function of xi by xi minus z d xi plus 1 by 2 pi I integration along PL. This is along LP and PL both. Function of xi by xi minus z d xi. This is equal to 1 by 2 pi I, this L M N L, this is along the curve C1, function of xi by xi minus z dxi plus 1 by 2 pi I, this is along LP. We may write also this along minus PL, function of xi by xi minus z dxi plus 1 by 2 pi I integration along PRQP. This means this is clockwise direction. We always take anti-clockwise direction, that is positive direction. So this will be along minus C2, function of xi by xi minus z dxi plus 1 by 2 pi I integration along PL, function of xi by xi minus z dxi. This is equal to 1 by 2 pi I integration along the curve C1, circle C1, function of xi by xi minus z dxi. We may write this minus here, minus 1 by 2 pi I integration along PL, function of xi by xi minus z dxi. We may write this minus sign here, minus 1 by 2 pi I integration along C2, function of xi minus z dxi plus 1 by 2 pi I integration along PL, function of xi by xi minus z dxi. Imply that function of z equal to 1 by 2 pi I integration along the circle C1, function of xi by xi minus z dxi. Here this and this cancel. This is negative sign, here positive sign, same thing. So remains minus 1 by 2 pi I integration along the curve C2, circle C2, function of xi by xi minus z dxi. Implies that function of z equal to I1 plus I2. This is number 3. This part is I1 and this part with negative sign is I2. Now let modulus of z minus z naught equal to r. Distance between z naught and z be r, and the radius of circle C1 is ρ1, the radius of circle C2 be ρ2, ρ2 less than ρ1. This is number 4. R by ρ1 less than 1 and row 2 by row 1 less than 1. This be number 5. Now we calculate I1, that is, we will find the integration along the circle C1. Let xi be arbitrary point on the circumference of the circle. C1. Therefore, equation of circle C1 will be modulus of xi minus z naught. Z naught be the point at the center of the circle C1 and xi be arbitrary point on the circle C1, and this will be equal to rho 1. Let this is number 6. Now for the circle C1, 1 by xi minus z equal to 1 by xi minus z naught plus z naught minus z, and this equal to 1 by xi minus z naught minus z minus z naught. We take common here, xi minus z naught 1 minus z minus z naught by xi minus z naught. Let this is number 7. Now modulus of z minus z naught by xi minus z naught on the circles C1, this equal to modulus of z minus z naught by modulus of xi minus z naught. Modulus of z minus z naught is r, and this is rho 1. R by rho 1, here we see less than 1. This is less than 1. Therefore 7 may be written as 1 by xi minus z equal to 1 by xi minus z naught 1 minus z minus z naught by xi minus z naught whole to the power minus 1, implies that 1 by xi minus z equal to 1 by xi minus z naught using binomial theorem. This will be 1 plus z minus z naught by xi minus z naught plus z minus z naught whole square by xi minus z naught whole square plus dot 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 plus z minus z naught whole to the power n minus 1 by xi minus z naught whole to the power n minus 1 plus z minus z naught whole to the power n by xi minus z naught whole to the power n plus z minus z naught whole to the power n plus 1 by xi minus z naught whole to the power n plus 1 plus dot 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 bracket closed, and this is equal to 1 by xi minus z naught plus z minus z naught by xi minus z naught whole square plus z minus z naught whole square by xi minus z naught whole to the power cube plus dot 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 plus z minus z naught whole to the power n minus 1 xi minus z naught whole to the power n. This multiply this whole to the power n plus 1 by xi minus z naught. We take common z minus z naught whole to the power n by xi minus z naught whole to the power n. Here remains 1 plus z minus z naught by xi minus z naught plus z minus z naught whole square by xi minus z naught whole square plus dot 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 implies that 1 by xi minus z equal to 1 by xi minus z naught plus z minus z naught xi minus z naught whole square plus z minus z naught whole square by xi minus z naught whole cube plus dot 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 plus z minus z naught whole to the power n minus 1 by xi minus z naught whole to the power n plus, firstly we write this, z minus z naught whole to the power n by xi minus z naught whole to the power n. Here 1 by xi minus z naught, multiply this bracket. Here also 1 by xi minus z naught, multiply this bracket, same thing. So for this we write 1 by xi minus z. Here 1 by xi minus z. Let this is number 8. Using 8 for finding the value of I1 in 3. Therefore I1 equal to 1 by 2 pi I integration along circle C1 function of xi multiply 1 by xi minus z. In place of this we write 1 by xi minus z naught plus z minus z naught by xi minus z naught whole square plus z minus z naught whole square by xi minus z naught whole cube plus dot 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 plus z minus z naught whole to the power n minus 1 by xi minus z naught whole to the power n plus z minus z naught whole to the power n by xi minus z naught whole to the power n multiply 1 by xi minus z dxi. We separate these. 1 by 2 pi I integration along the circle C1 function of xi by xi minus z naught dxi plus we take z minus z naught outside. 1 by 2 pi I integration along the circle C1 function of xi by xi minus z naught whole square dxi plus z minus z naught whole square multiply 1 by 2 pi I integration along the circle C1 function of xi by xi minus z naught whole cube dxi plus dot 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 plus z minus z naught whole to the power n minus 1 1 by 2 pi I integration function of xi by xi minus z naught whole to the power n dxi plus z minus z naught whole to the power n multiply 1 by 2 pi I integration along the circle C1 function of xi by xi minus z naught whole to the power n multiply 1 by xi minus z dxi. Here variable be xi, so we may take z minus z naught whole square outside the integration. Implies that I1 equal to, let this is A naught plus this part is A1 z minus z naught plus A2 this is A2 z minus z naught whole square plus dot 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 plus last is Rn. Let this is number 9. Since function of xi is analytic on the circumference of the circle C1, therefore modulus of function of xi less than m1, a positive integer. That is, this function is bounded on the circle C1. Let this is number 10. Since Rn equal to z minus z naught whole to the power n multiply 1 by 2 pi I integration along the circle C1 function of xi by xi minus z naught whole to the power n multiply 1 by xi minus z dxi implies that modulus of Rn equal to modulus of z minus z naught whole to the power n 1 by modulus of 2 pi I modulus of integration along C1 function of xi by xi minus z naught whole to the power n 1 by xi minus z dxi and modulus. This is less than equal to modulus of z minus z naught is r to the power n multiply 1 by, here modulus of I is 1, so here remains 2 pi. Here we have given this side greater than equal to, because this modulus will enter inside the integration, means integration C1 modulus of function of xi by modulus of xi minus z naught whole to the power n 1 by xi minus z modulus of dxi less than equal to r to the power n by 2 pi. This is less than equal to m1 xi minus z naught. Xi is on the circle C1. Xi minus z naught is rho 1 to the power n and 1 by plus of xi minus z dxi modulus. Let this is number 11. Since xi minus z equal to xi minus z naught plus z naught minus z, this is equal to xi minus z naught minus z minus z naught, implies that modulus of xi minus z, this is greater than equal to modulus of xi minus z naught minus modulus of z minus z naught, and this is equal to modulus of xi minus z naught is rho 1 minus this is r. This is number 12. Using 12 in 11 we get modulus of Rn less than equal to R by rho 1 to the power n multiply 1 by 2 pi multiply m1. Here we take outside this outside. This means 1 by rho 1 minus r modulus of dxi. Since in place of this we have written this, so this is lesser quantity. If we give lesser quantity in denominator, then right side will be greater, implies that modulus of Rn less than equal to 1 by rho 1 minus r multiply r by rho 1 to the power n multiply 1 by 2 pi m1, and integration of this is modulus of dxi is the circumference of the circle C1 2 pi rho 1. This tends to 0 as n tends to infinity. Since r by rho 1 is less than 1, if we raise the powers of a quantity which is less than 1, this tends to infinity, then it will be lesser and lastly 0. Implies that Rn equal to 0. This is number 13. Using 13 in 9, we get I1 equal to A0 plus A1 Z minus Z0, A2 Z minus Z0 whole square plus dot 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 and lastly 0. This will be equal to sigma n equal to 0 to infinitive an z minus z0 to the power n, where an equal to 1 by 2 pi I integration along the circle C1 function of xi by xi minus z0 whole to the power n plus 1 d xi.